It's worth noting that the numbers in Pascal's triangle don't just appear out of nowhere. Those numbers that serve as the coefficients in binomial expansion are the result of using the combinations formula, used for counting the number of possible subsets of a larger set of elements. And so if we have kind of a very formal structure for binomial expansion, what we'll see is the x's are going up in exponent from n and working their way down. The y's are going up in exponent from y to the 0 up to y to the n. And then the coefficients eventually can be represented by this NCR expression. This is the combinations expression, which translates into n factorial over n minus r factorial times r factorial, where n is the number of numbers from which we're choosing, and r is the number of numbers in the subset that we're selecting. So we can represent this several different ways. We can write it in this NCR format. We can write it in this parentheses format where it's C and then n comma r on the inside, or it could be written in this kind of stacked format here. And so the bottom line is we're going to be using this factorial expression here to calculate with whatever numbers n and r equal. So in this first one, n would be 8, r would be 6. So in our expression, we're going to have 8 factorial over n minus r, so 8 minus 6 is 2 factorial, and then times r factorial, which is 6 factorial. Now we do have to make sure that we're cautious about how we simplify here. Remember, the numerator we can write out as 8 times 7, 6, 5, 4, 3, 2, and then we don't need to put the 1. And then on the bottom here, we've got 2 times 1, or just 2, and then we've got the 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1. And so now, once we see it like this, we can start to do our cross-canceling reducing. So we've got a 6 times 5 times 4 times 3 times 2 on the top, and the same thing on the bottom. And then we've got the 2 can divide evenly into 8 to leave us with 4. And so all we're left with is 4 times this 7 right here. So our answer for the expression here of the number of combinations of 6 items from a pool of 8 is 28. In the second example, so we've got different format, but the same formula applies. So our n value is going to be 7, our r is 2. So I plug those into the formula that we see right here. We have 7 factorial over n minus r, so 7 minus 2 is 5 factorial, and then we've got the r factorial, which is 2 factorial. And so then if we do our cross-canceling reducing, hopefully kind of in our head, we can see that 7 factorial over 5 factorial is going to reduce to 7 times 6, because the 5 times 4 times 3 times 2 is going to cross-cancel from the top and the bottom. And then 2 factorial is just 2, so we can reduce the 2 and the 6 to give us a 3. 7 times 3 is 21. Last expression, we've got 9 over 0. And so if you'll recall, I've mentioned that 0 factorial equals 1, and here we're going to see evidence of why that's necessary. So in this case, my n is 9, my r is 0. So in my expression here, we've got n factorial, so 9 factorial over n minus r, so 9 minus 0 is 9 factorial, and then r factorial is 1, or 0 factorial, so that's just going to equal 1. So if that equals 1, then we just have 9 factorial divided by 9 factorial, which equals 1. And so each of these expressions corresponds to a coefficient or a number in Pascal's triangle, or a coefficient in our binomial expansion. So for example, when we look at C8, 6, we go to the 8th row of Pascal's triangle, starting with the top row being 0 and working our way down. And if we count inwards from the first term being 0 to the 6th term, we would see that that number in that row in that position would be 28. In the 7th row of Pascal's triangle, counting from 0 at the top down to the 7th row, and then counting inwards 0, 1, 2, so that second term, the 0 first, second term, would have a value of 21. And then likewise, the 9th row, the first entry into any row of Pascal's triangle is 1. So these numbers correspond with the appropriate location in Pascal's triangle and then serve as the coefficients of the binomial expansion.